Welcome everyone to the Math Colloquium. Today we're very happy to have Professor Jang Kim from Sungkyunkwan University who will speak about combinatorics of symmetric functions. Let's welcome Professor Kim.
Thank you very much. Thank you for the invitation. So today I'm going to talk about combinatorics of symmetric functions. I prepared my talk so that it is accessible to people who are not expert in combinatorics. So let me show you the overview of the talk. I first tell you a little, some motivating question, quite simple one, and then the main topic is about symmetric functions. And there are many symmetric functions, but we will be focusing on one class of symmetric functions called short functions. And these short functions have many interesting combinatorial properties, and we will be focusing on one of them called Jacobi-Trulli formula, and I'm going to show you how to prove that theorem using what's called LGV lemma. And if I have time, I'm going to tell you a little bit more about growth-ending polynomials, which are basically generalization of short form. And if I have time, I'm going to tell you a little bit about what I did on this refined canonical stable growth-ending polynomials. All right, so first, let me begin with a very simple high school math problem. When I was young, when I was a high school student, I really saw a problem like this. So let's see. Suppose that x plus y plus z equals a, xy plus yz plus x equals b, xyz equals c. And the problem is, there are three expressions, and the problem is to express each sum as in terms of a, b, and c. Have you seen a problem like this in high school? Because the material we learn in high school have been changing quite a lot over a few decades. So I'm not sure if they still learn this, but when I was young, I learned this in high school. So let's do this. The first one is trivial. It's already in A. Second one, we know that if we square x plus y plus z, then we get this form. Then this is we want to express this, but this is A, this is B, so we know how to express that. It's more complicated, but we know how to do that, right? We make a cube of this, and then this part can be obtained if you multiply these two, and then we get a formula then. So we know how to express this as in terms of A, B, and C. So if you are a high school student, you will be satisfied right now. But if you're a mathematician, you will be asking more questions. Can we do this with like x to the 10th power, etc.? In general, can we do this for arbitrary integer n? Can we express this in terms of A, B, and C? And I'm going to give you an answer a little later. And to answer this, I'm going to tell you some definition. So a polynomial, multivariate polynomial f with n variables is symmetric if it is invariant under any permutation of the variables. So if you permute the variables any way you want, if the value does not change, then it is called symmetric polynomial. So for example, these are all symmetric. If you permute x1, x2, x3, you don't really change the polynomial. But this is not symmetric because if you permute x1 and x2, and you see that this term x1 squared x2 is not here. So this is not a symmetric polynomial. And there are many interesting symmetric polynomials, but probably one of the most well-known one would be elementary symmetric polynomials. So the kth elementary symmetric polynomial is with n variables. It's just a sum of all monomials obtained by taking k distinct variables. Okay. So for example, E1 is if you have 3 variables, then it's just this because you take only 1 variable. E2, you take 2 variables, 2 distinct variables, then there are 3 terms like this. And E3, there is only one way to select 3 distinct variables, is this. And if
Type or E2.
oh, yeah, that's right. Yeah, it should be 1, 3. Yeah, thank you. And E4 is 0 because we have to select 4 distinct variables, but we have only 3, so it's 0. But of course, if we have more variables, this will be non-zero. And these elementary symmetric polynomials are closely related to the roots of a polynomial. So we know that if we have a quadratic polynomial, and if alpha beta are the roots, then we know that the coefficients can be written using in terms of the roots like this. And for the cubic polynomial, if the roots are alpha, beta, gamma, then we can also write the coefficients using the roots. And in general, if we have a degree n polynomial with a leading term 1, leading coefficient 1, and if alpha 1 up to alpha n are the roots, then the coefficients are really just the elementary symmetric functions, symmetric polynomials up to sign, right? So, and now I'm gonna consider symmetric functions. These are really the same thing as symmetric polynomials, but basically they have infinitely many variables. First, I'm going to define this partition. So partition is a weakly decreasing sequence of positive integers. And each lambda I is called a part. And the length is the number of parts here. And the size is the sum of the parts, and is often denoted by this absolute value sign. And if the size is n, then we say that lambda is a partition of n, and then I'm going to use this notation. And PEAR is the set of all partitions, and PAR of n is the set of all partitions of n. So for example, empty partition is also considered. It's a partition of 0. This is only partition. Part of 1 is this, and etc. Here I use the just like this is just a sequence 1, 1. Just for short brevity, I wrote this way. And the Young diagram of a partition is just an array of boxes, so that ith row has lambda I boxes, and they are left justified like this. So if lambda is 4, 3, 1, we have 4 boxes in the first row, 3 boxes in the second row, and 1 box in the third row. And the conjugate of a partition is just a partition whose Young diagram is obtained by the Young diagram of the original partition by reflecting it about this main diagonal. So in this case, the conjugate is going to be this. The Young diagram is this. So it's 3, 2, 2, 1. Okay. And now let me define symmetric functions. So now x is going to be a sequence of variables and infinitely many variables like this. And a formal power series in these variables is a symmetric function if we have the same condition as before. We permute the variables. There are infinitely many variables, but we can still permute them. And no matter how you permute them, the formal power series is still the same. Then it is a symmetric function. It's really like a symmetric polynomial with infinitely many variables. And people sometimes don't really distinguish symmetric functions with symmetric polynomials. Sometimes just call everything as a symmetric function. And we can also understand this in this way. What is a formal power series? A formal power series means we have it's like a polynomial. We add the various terms. And the formal power series is really like a way of recording these coefficients. So here alpha is a sequence of non-negative integers. but finitely many non-zero terms, of course. And the x to the alpha means x1 to the alpha 1, x2 to the alpha 2, okay? And the coefficient, if the coefficient is C alpha, then this is a symmetric function, depend only if you compare two monomials, two monomials, x beta and x beta, x to the alpha and x to the beta, their coefficient must be the same. This is exactly the same condition as this being symmetric. So for example, by the way, I'm gonna denote the space of symmetric functions of homogeneous degree n by this lambda n, and just lambda is the direct sum of all of it. So this is the space of all symmetric functions. So for example, if I define this f of s in this way, so all distinct ij indices I and j, I'm gonna add xi squared xj. Then I listed some of the terms, like we may have terms like this or this and etc. This, if you look at this by definition, it is quite clear to see that it's a symmetric, and it's a degree 3, a homogeneous degree 3. The degree means we consider xi, each xi contributes degree 1. And in this case, using this notation, if alpha is this sequence and beta is this sequence, then C alpha is 1 because this is a bit hidden. But this means x1 raised to the first power, x2 to the raised to the second power, like this. And if you look at this, the coefficient is 1, that means C alpha is 1. Also, C beta is 1 because this means that x2 squared x4 to the first. Okay, so you see things like this. So this is the main object in this talk. And there are many useful bases for this space, and probably the simplest one would be monomial symmetric functions. So suppose that lambda is a partition, then the monomial symmetric function indexed by lambda is just the sum of all monomials x to the alpha, x raised to the alpha, where alpha is over all distinct permutations of this sequence. So we started with this lambda, but I'm gonna attach zeros at the end to make it an infinite sequence. And there are many, infinitely many ways to permute them. And for all distinct permutations, I'm gonna add this monomial. Okay. So for example, by the way, if lambda is empty, this is just defined to be 1. And if lambda equals 2, then you permute 2, 0, 0, 0. So everything looks like 0, 0, 0, and 2 at some point, and then 0. So they contribute xi squared. 2, 1, 1. Because we have 1, 1, these two numbers are equal, we have to consider I less than j. Because like if I is less than j, then this must be added only once, because we don't consider xj, xi as a different, because these two are the same permutation. If you permute 1, 1, then what really matters is the positions of these ones, because 1 and 1 are equal. But on the other hand here, 2, 1, these are distinct, so we consider all ij different. So it looks like this. So these are examples of monomial symmetric function. So theorem is the monomial symmetric functions for all lambda partition of n. This is a basis of the space of symmetric functions of degree n. And this is actually, so that means the dimension is the number of partitions, this is the number of partitions of n. And if you consider all partitions, this is going to be a basis for the whole space. Okay. And the proof is quite simple, because whenever you have a symmetric function of degree n, then you can always write in this way. And because the coefficients are equal, if the alphas are permuted with others, this is really the same thing as the sum for all. We can combine all x to the alpha for alpha permuted, then we get just a partition. It's the same thing as considering this monomial symmetric function, and the same, you can just attach the same coefficient over here. So this is basically just a one-line proof. So we know one basis of the symmetric function, and I'm going to introduce some more. The elementary symmetric functions, E lambda, where lambda is again a partition, is the product of E lambda 1, E lambda 2, dot, dot, dot. Yeah. Where E d for an integer d is exactly the same thing as we saw before. Only the difference here is that there are infinitely many variables. So we select d distinct variables among the infinitely many variables x1 of dot, dot, dot. And then, so ed is defined like this, so that we can define E lambda. And homogeneous symmetric functions are defined similarly, denoted by h lambda, exactly the same way, except here we may select one variable more than once. So here we choose d variables with multiplicities, with possible multiplicities. That's the only difference. Okay. And power sum symmetric functions are defined similarly, but PD is x1 to the d plus x2 to the d, etc. And by definition, these are all symmetric functions. You can quite easily check. And the theorem is these are all bases. They all form a basis of the symmetric function space. So far we have seen 4 bases of the symmetric function space. Oh, now I can answer the question that I raised at the beginning. So we had this problem. Can we express this in terms of A, B, and C? And now we're going to consider this symmetric function space, but I'm going to substitute these variables to be x, y, z, and zeros. So we have only 3 variables now. And obviously, this is a symmetric function in this space. Okay. And because this is a basis, this must be written as a linear sum of E lambda for all partition lambda. But this means E lambda 1 times E lambda 2 times dot, dot, dot. But if k is greater than 3, we know that the kth elementary symmetric function is 0 because you cannot choose more than 3 variables. So that means the terms that survive here are only those with like E1, E2, E3. They are exactly like A, B, and C. That means we should be able to write this as a polynomial in ABC. It doesn't tell you how to write this as a polynomial in ABC, but it says that it is possible. So if you are a high school teacher, you can always make a problem like very easily because it's always working. All right. Now I'm gonna focus on Schur functions. So let me begin with the definition. Again, lambda is a partition, but the number of parts is less than or equal to n for a fixed integer n. But here, this is a common convention. If the n is greater than the length, then I'm going to assume that there are some zeros appended at the end. So that because I want to somehow say lambda I for I greater than L. If I is greater than L, lambda I is going to be 0. So the Schur polynomial with n variables is defined to be the ratio of these 2 determinants. This is the Vandermonde determinant, okay, the denominator. The numerator is a bit different. But if you look at the determinants carefully, then you will see that it is a symmetric polynomial. Because if you permute, for instance, 2 variables, xi and xj, and because this j, this means the jth column, if you switch xi, xj, that means you switch column I and column j. So then the determinant will be minus of that one. And again here, if you change xi, xj, then we still have a minus sign here. those will be cancelled. So the whole thing is going to be invariant. So it is a symmetric function, symmetric polynomial. So yeah. And you can actually check that if there are more variables, like suppose that there are n plus 1 and put it into this definition, and if you substitute xn plus 1 equals 0, then it's the same thing as this one. And if you have a condition like this, then we can define the short function with like infinitely many variables using the inverse limit. This can be done because of this property. If you are not familiar with the inverse limit, that's okay, because I'm going to give you a different definition, right? Equivalent definition. And the fact is, this is also a basis for the space of symmetric functions on the N. And short functions are considered to be the most important symmetric functions for various reasons. First of all, this symmetric polynomial is the character of an irreducible representation of a general linear group. And short functions encode irreducible characters of the symmetric group as well. And there is a map called the Frobenius map, which is an isomorphism between the class functions of Sn and the space of symmetric functions. And it sends the irreducible character to the short function. So this means that understanding the representation of Sn is more or less the same thing as understanding symmetric functions in terms of short functions. And they also have like some geometric meaning, some cohomology classes of Schubert varieties, the Grassmannian, and there are many interesting combinatorial properties. And they have many interesting and nice properties. Like there is an important inner product called the space of symmetric functions called the whole inner product, and the short functions, they form a self-dual basis to this. And also there is an involution usually denoted by omega, and this omega involution sends the short function to another short function. The only difference is if you take the transpose. The very nice properties. And because short function is a symmetric function, there must be a way to express this in terms of homogeneous symmetric functions or elementary symmetric functions. And there are nice formulas like this. These are called Jacobi-Trudi formulas. And I'm going to show you one proof of this, which is very common.
What is the definition of the whole inner product?
Actually, you can take this as a definition. Okay. But normally the definition is like here m lambda h lambda. So usually I think it's more common to define the whole inner product using this.
Okay. And this is equivalent to
right, the equivalent definition. Yeah. Any other questions so far? Okay. Now I'm gonna do some combinatorics. A semi-standard Young tableau is of a shape lambda for a partition. Lambda is a filling of the Young diagram with positive integers with these properties. So if you read every row, it must be weakly increasing. And if you read every column, it must be strictly increasing. Okay, just like this. And the standard Young tableau is basically the same thing, except we have exactly 1, 1, exactly 1, 2, etc. So it's a special case of a semi-standard Young tableau. And SSYT is the set of semi-standard Young tableau of shape lambda, and similarly for SYT. And yeah, I'm going to use this notation as well. And this short function, this can be also considered as a definition of a short function. It's equivalent to the original one that I mentioned. The short function S lambda can be defined in this way. So now you have infinite many variables. This is a generating function for all semi-standard Young tableau of shape lambda, x sub t, which is x1 to the number of ones, x2 to the number of twos, etc. in this tableau. So for example, this is a semi-standard Young tableau, and the weight of this, which is denoted by x sub t, x1 to the number of 1s, which is 2 here, x2 to the number of 2, which is 3, x3 to the number of 3s, 2, x4 to the 1, like this. So you consider all semi-standard Young tableau of this shape, and then you add monomial. That is going to be an infinite sum, it's a formal power series. That is exactly the short function. So this is a combinatorial definition, and it can be proved that these two are equivalent. And if there are finitely many variables, and then this is going to be a polynomial. So in this case, the shape is 2, 1, 2, 1, and there are only two variables that we are only allowed to use integers 1 and 2. And you can see there are only two semi-standard Young tableau like this. And you see this contributes to this term, this contributes to this term. And in fact, if you look at this definition, then you will be wondering the following, because the definition, in this definition, is not clear whether this is a symmetric polynomial. Symmetric. If you permute the numbers, then you cannot simply permute the numbers here because it's not going to be SSYT. So it's not clear, but it can be proved using a nice combinatorial involution. It's called Bender-Knuth involution, but I'm not gonna give you the details. But it is possible to prove the symmetry using just the combinatorics. And the Jacobi-Trudy formula, I showed you this earlier. It looks like this. Short function is the determinant of some homogeneous symmetric functions with some, these are like just a single integer. It's not a partition, right? The lambda is a partition, of course, but this is lambda sub I, so this is just a single number. And I'm going to show you a proof of this because I think it's very interesting. And I'm going to use what's called Lindstrom-Gesell-Vienna lemma. And have you heard of this book called Proofs from the Book? Or have you heard of the book? So maybe you heard this story. So Eldridge, he used to say that like there is a book in the heaven that has like all the beautiful theorems and all the beautiful proofs. So we as mathematicians, our duty is to find the proofs from the book. And you know, so these two people, they wrote this book. So you know, of course, we don't know if there is such a book. So they collected what they believed the most beautiful proofs, and then they wrote a book, which is very interesting. There are many interesting theorems and proofs, and Lindstrom-Gesell-Vienna lemma is one of them. It's a chapter 32. So at least they believe that this is really a beautiful theorem, and I agree. And I'm going to show you this. At least a statement and how to use this to prove the Jacobi-Trudy identity. So we need some setting. So G is a directed graph, and a path is like a usual term in graph theory. It's a sequence of vertices such that if you go from Vi to Vi plus 1, it must be an edge, directed edge. And this is a set of all paths from U to V. The starting point is U, ending point is V. And we're going to assign some weight to each edge. So the edge weight is just a function from the edge set to some commutative ring. And the weight of a path is going to be the product of the weights on the path. So for example, actually, in this talk, we only need this graph. So the graph is just a grid, z squared, but the directions are like up, above, or to the right. It goes to either to the right or above. And the weight, the up steps all have weight 1, and horizontal steps, if the height is I, then the weight will be x sub I. So here in this is a path from 1, 0 to 4, 4. And because we have like horizontal steps like this, whose weight are like x1, x3, x3. The weight of this path is x1 times x3 squared. Okay, so this is the setting. And the Lindström-Gessel-Vienna lemma. I need one more notation. So now this boldface A is a sequence of points or vertices, and B also a sequence of vertices in the graph. And P of A to B is a set of all n paths, meaning the n tuple of path, such that, so basically these are the starting points and these are the ending points. But there are no restrictions which AI should go to which BJ. They can go anywhere as long as one, there are no like every AI must go to BJ without a collision at the beginning or at the end, meaning that every ith path must be a path from AI to B of sigma I for some permutation sigma. That means the ending points can be permuted in some way if you go from AI. And the weight of this n path is the product of the all path. And I'm going to also define the sign of this n path, which is just a sign of the permutation. Okay. And ni of A to B is a set of all non-intersecting n path. Here, non-intersecting means any two paths do not share any common vertices. Okay. And the lemma, the Lindström-Gessel-Vienna lemma is the following. Suppose that we have a matrix whose entry Mij is the generating function for all paths from Ai to Bj. Okay, and then the determinant is equal to the generating function for all non-intersecting paths from A to B with this sign. Let me give you an example. So again, we have the grid, and for simplicity, I'm going to define the weight all to be 1. And let's say A1, A2, and B1, B2 are given like this. So A1, A2, and B1, B2. So what is the matrix? The ij entry must be the number of paths from Ai to Bj. So 1, 1 means, this entry means the number of paths from A1 to B1. So this is like 3 choose 1. And this means number of paths from A1 to B2. So this is 4 choose 2. And similarly here, is number of paths from A2 to B1. So this is number of paths from A2 to B2. So if you compute this, you get 3. And the Gessel-Vienna, the LGB lemma says that this number is exactly the number of paths from these points to this point without any intersections. And there are some signs attached, but if you have non-intersecting path, A1 must go to B2, B1, A2 must go to B2. So the permutation is always identity. The sign is always 1 for non-intersecting lattice path. So there are exactly 3 non-intersecting paths. That's the 3. So that's what the LGB lemma holds in this example. But in fact, you can prove this directly by understanding the meaning of each term. So for instance, suppose that you don't know the LGB lemma and you want to count number of paths from A's to B's without any intersection. How would you count? Yeah, we know that A1 must go from the path from A1 must end at B1. Path from A2 must end at B2 in order for them to be non-intersecting. So just count all paths from A1 to B1 and all paths from A2 to B2. And that is exactly this term. But then we counted too many because there are some intersections. And the intersections can be understood in this way. Whenever we have an intersection, we can change the pairs after this intersection. And then this is the same thing as the number of such intersecting path is exactly the number of paths from A to B2, A1 to B2, and A2 to B1. Here I just swap the pairs after the intersection. Then the ending points are swapped. So the sign as a permutation, the sign is minus. So that's exactly this. So for n equals 2 case, you can prove this LGB lemma like this. But for general n, the same idea works. You only need to consider like some kind of how to choose the somewhat minimum intersection or something like that. Basically, the same idea, using the same idea, you can prove the LGB lemma. All right. Now I can prove Jacobi-Trudi identity using this LGB lemma. By the way, I'm going to only prove this. This can be proved similarly, but a bit different. But I'm going to prove this Jacobi-Trudi formula. And to do this, let me sketch the idea first. By the way, we have infinitely many variables, but we may assume that there are only finitely many variables up to capital N, because we can always send n to infinity in a rigorous way. So, and we're going to use the same graph and the same weight, like horizontal step has weight xi if the height is I. Up step is always 1, has weight 1. And you can see that this homogeneous symmetric function, the k homogeneous symmetric function, is really the generating function for lattice path. Let me show you this example. In this case, if you compute this homogeneous symmetric function with 3 variables, then we know that should be this. But each term corresponds to exactly one path from 0, n to k, n. 0, 1 to k, n. Here, because here we have, in this example, we have 6 terms, 6 paths. And see, this corresponds to x1 squared, this corresponds to x2 squared, etc. And if you think about it, if you want to go from here to there, then if you look at the height of horizontal steps must be always weakly increasing, right? Because you cannot go down. So that's exactly the same thing as the homogeneous symmetric function. So this is nothing but the lattice path generating function for 0, 1 to k, n. And in fact, because the x coordinate do not really matter, we can freely shift the starting and ending points anywhere we want. All right, so this is the crucial observation. Now we have all the settings, so we can prove Jacobi-Trudi formula. So the setting is that I'm going to define AI to be this. Maybe I can just show you the diagram. So given lambda, A1, A2, A3 are put like this, like n minus I, comma I. So these are all consecutive like this. And for ending points, B1 is lambda 1 plus n minus 3. So n equals 3 here, that's lowercase n. So this is 6. And this lambda 2 minus, lambda 2 plus n minus 2, which is in this case 4. And then the third one is going to be this. So we fix the starting points and ending points like this. And by the definition of the determinant, this, if you think about it, this is exactly the difference between the x coordinate of B, I, A, J. That means this is the generating function for lattice path from AJ to BI. Is that right? So we are exactly in the situation in the LGB lemma. So this is a generating function. The LGB lemma says that this is a generating function for all non-intersecting lattice path from A's to B's. But because of the ways they are arranged, if you want to have a non-intersecting lattice path, A1 must end at B1, and A2 must end at B2, etc. So that means the permutation is always the identity So the sign is always plus. So we have this non-intersecting lattice path, but this is nothing but a semi-standard Young tableau. The way I construct a semi-standard Young tableau is the following. We have the first path. I'm going to read the indices here. So 1, 1, 2, 3. So I'm going to put them in the first row. And then I'm going to put the indices in the second path in the second row, 2, 2, 3. And then I'm going to put the indices in the third path in the third row, 4. And by the way, this is non-intersecting. These are must be strictly increasing. And because this is a lattice path, each row must be weakly increasing. And this is indeed a bijection. And the weight here is exactly the weight over here for the semi-standard Young tableau. So what we get over here is that the left-hand side, the determinant is equal to the generating function for all non-intersecting lattice paths. And this is the same thing as the generating function for semi-standard Young tableau, which is the short function. This is the proof of the Jacobi 2D formula using LGB lemma. And the other formula can be proved similarly, but we have to modify the graph a little bit. So I'm not going to do that, but it can be done. Any questions so far?
Sorry, can you explain again how you go from the non-intersecting lattice path to the semi-standard Young tableau?
Yeah. So this is the first path, A1 to B1. And you look at the labels here, like 1, 1, 2, 2.
I see. So that's the first row in the
Right.
semi-standard.
And because it is always going up, so the labels are always weakly increasing. That's why each row is weakly increasing. And the fact that these are non-intersecting, it must be strictly, each column must be strictly increasing. So this naturally correspond. Right. And there are many generalizations of the idea like this. Or there are many like Jacobi 2D type identities. All right, now let me tell you a little bit about grothendieck polynomial. The short functions have many generalizations. So I was thinking which generalization I should mention here, and I decided to talk about grothendieck polynomials because I've been working on this quite a lot recently, and Valentine have also done some work in this direction. So yeah, I think it might be interesting to you. The grothendieck polynomials. There's a little bit of history about the grothendieck polynomials. First of all, grothendieck polynomials are indexed by permutations, not just partitions. So there are more indices than short functions. And this was first introduced by Lascaux and Schutzenberger more than 40 years ago. And they introduced this when they were studying structure shift of Schubert varieties in a flag variety. So there's some geometric motivation. And stable grothendieck polynomials are some special case of the original one, introduced by Fomin and Kirillov. And if I remember correctly, this is not a symmetric function, but it is a symmetric function. And now still it is indexed by permutation. And if you consider, but we can also focus on specific grothendieck polynomials, like a grothendieck type, then they are now indexed by partitions. And they form a basis of the symmetric function space. And Book, he found a combinatorial model for this using something similar as what's called a set value tableau, which are similar to SSYT. I'm going to show you what these are. And there are also dual version of stable grothendieck polynomials. Dual in the sense that capital G and small g, they form dual basis with respect to the whole inner product. But you see, once you have, if you start with one basis, and you can always ask, what is the dual basis? But for the sure case, you don't get anything new because sure is self-dual. But in this case, this is not self-dual, so we can talk about this dual basis. So that's how they consider these symmetric functions, small g. And there is also a nice combinatorial model for this. And let me,
Sorry,
yeah.
quick question. These Grothendieck polynomials, can you think about them as just some Q generalization of Schubert polynomials?
What generalization? Q?
Q or beta or something?
Oh, yeah, right. That's right. And actually, they had beta, parameter beta here. I didn't mention, yeah.
Okay.
So one single variable parameter there. But that's a good question because I'm gonna add more parameters here.
Okay.
And let me tell you the combinatorial models. The short function, we know that's the sum over all SSYT. So it's a filling of this Young diagram with these conditions. And set value tableau are interesting objects. Instead of putting an integer in each box, we're gonna put a set. So that means we can put more than one integers. But because it's a set, the integers must be all distinct. So this 1, 2 means the set consisting of 1 and 2. Okay, so this is 2, 3, and etc. But the condition is still the same. If you read each row, weakly increasing, considering all the elements in that set. But if you read each column, must be strictly increasing. So because there is a 2, you cannot have a 2 over here. Okay, and the weight is the same. Number of ones for x1, number of twos for the power of x2, etc. So if you don't allow like more than one element in each set, is exactly like this. And dual Grothendieck polynomials generating function for what's called reverse plane partition, but it's really it's quite similar to SSYT, except in both directions, weakly increasing. But the weight is a bit different. Instead of having this x1 to the x number of ones, it's going to be x1 to the number of columns with 1. So in this example, there are 2 columns containing 1. So it contributes x1 to the second. It's not like x1 third, x squared. And there are 2 columns containing 2, so x2 squared. 1 column containing 3, so x3. And 1 column containing 4, x4. Okay. Actually, it's not really relevant for the rest of this talk, but you may wonder, why don't you just have like the same weight here, x1 to the number of ones, x2 to the number of twos, etc. You can consider that, of course. But the interesting thing is that is not a symmetric function, which is, I think, quite interesting because this one seems more symmetric than this, they are not quite symmetric. I mean, the conditions here, very symmetric, both conditions. But if you do that, the resulting object is not a symmetric function. But this is symmetric. Anyway, there are. Yeah.
But when you define Grothendieck polynomial, what do you mean by inequality between sets?
Oh, yeah. So that means this holds if you select any element in that set. So in other words, the maximum element here must be less than or equal to the minimum element here. So compare everything is increasing, weakly increasing. And same here. Yeah. Okay. And now there are generalizations of these Grothendieck polynomials. I'm gonna tell you some history. The refined stable Grothendieck polynomials, RG, we have a beta index, but this is actually infinitely many parameters introduced by Chan-Floger, and they also had some motivation from geometry, which I'm not gonna tell you about. And they have also a nice combinatorial model. The object is exactly the same, the set value tableau. But the condition is still the same, but only the weight is the different. Of course, we must have some beta over here. The beta follows the number of extra integers in each column. So beta 1, the power of beta 1 is the number of extra integers in column 1. By extra means, usually for SSYT, each cell contains one element. If there are more than one, then you count that counts as an extra element. So in this example, in the first column, there are 1, 2, 3 extra elements. So it's x1 to the third. In the second column, there's only one extra element, so x2 and beta 2, and one element of beta 3, and one extra element beta 4, like this. And there are also refined dual version of this with infinitely many parameters introduced by these 3 people. And they also have this nice generating function in terms of RPP. Again, the same object, same way, except now beta counts the number of equalities between row 1 and row 2. That means here, how many equalities do we have between row 1 and row 2? Equality means like a 2 in the same column. That are equal. So here we have 1 equality, 1 equals 1. This is not equal. 2 equals 2. So we have 2 equalities here. That means we have beta 1 to the second. And then there are no equalities between row 2 and row 3. So beta 2 does not appear over here. But anyway, the interesting thing here is that these 2 objects have been introduced by 2 groups of people in completely different way, but they are dual to each other, which is, I think, quite interesting. And you see that these are generalizations of short functions, because just say that suppose that all the b's are 0. That means you cannot have extra elements here. That means everything is just every cell has one element. So it's exactly like SSYT. So this becomes a short function. And same here, no beta means no equalities if you read columns. So the column is strictly increasing. So again, this becomes a short function. So both are generating generalizations of the short function. Now, canonical. Now let me summarize what we have seen so far. So we have this Grothendieck and then dual, and we have refined versions like this, like beta, infinitely many betas. Then these are also duals. And there is also an involution called omega involution. If you apply this, then we get different symmetric functions. And for the short function case, if you apply omega, then it's still a short function. Although lambda is changed to lambda prime, it's still a short function. So as a family, you don't get anything new. But here, we may get something new. But instead of considering this, Yelyusijov was wondering, can we modify this so that it has similar properties as the short function? The Grothendieck becomes Grothendieck with lambda prime. So because of this motivation, he defined these canonical stable Grothendieck polynomials as this ratio. It looks similar to the short function, if you remember. But you see, if alpha and beta are 0, then this term just disappears. So it's exactly like the short function. It's a generalization of short function with 2 parameters, alpha and beta. These are not infinite sequences of parameters, just 2 parameters. And there are dual versions like this. And so he showed that we have somewhat expected properties, although we have to change a little bit, but still in the same family. So in summary, we have these connections, Grothendieck and dual and refined, canonical, AB, and alpha, beta. Okay? And this has infinitely many variables, beta and beta. So our motivation was that, can we generalize this to infinitely many variables, alpha, beta, so that we have something over here that generalizes everything. That was our motivation. So we defined refined canonical stable Grothendieck polynomials here. here both alpha and beta are infinite parameters. So they are like really somewhere fitting over here. That generalize everything. And I'm not gonna tell you the whole everything, but let me just tell you how the formula looks like. So we defined the canonical stable growth-ending polynomial with infinitely many parameters alpha and beta in this way. And in fact, if alphas are all equal to alpha, just alpha, if betas are all equal to just beta, then this reduces to Eleusirov's formula. And in fact, I'm not going to tell you the details, but it is possible to rewrite this using what's called a platistic substitution. And we also defined a dual version similarly. And we showed that these growth-ending polynomials have many interesting properties. It generalizes like Shor function, many properties of Shor functions in a natural way. Like a growth, we have these Jacobi-Trudi formulas and duality, and omega involution has these nice properties. And then we also show that these are Shor positive, which means that because this is Shor symmetric function, we should be able to write this as a linear sum of Shor functions. And the coefficients are non-negative polynomials in the parameters. That's what a Shor positive means. And we have combinatorial models. And let me just tell you, without details, the object is marked multi-set value tableau. So before we saw set value tableau, so each cell is filled with a set, but now it's a multi-set. We may have like multiple elements, and we have some rule to mark some entries there. So the generating function is basically objects like this. We have, but with the same condition, weakly increasing and strictly increasing. And it generalizes like everything that we have seen so far. And for dual version, we have similar things with some markings. And I'm near the end of the talk, so let me tell you some open problems. For Shor functions case, we can multiply two Shor functions. Again, it's going to be a symmetric function. So we can express this as a linear sum of Shor functions, and this coefficient, oh, I forgot, this is typo, it should be lambda comma mu here. This number is called the Littlewood-Richardson coefficient. There are nice combinatorial descriptions for this. And we don't know how to, we don't know anything about this in general. So, but I think in Littlewood-Richardson coefficients are something that's not very easy to compute. So I think this is a project that we don't know what to do so far. But I think if you can find some combinatorial interpretations for this, I think it will be very nice because it generalizes many objects. And I think, yeah, that's it. Thank you very much.
Thank you for the last part. Are there any questions or comments? So I have a few questions. So these Littlewood-Richardson coefficients that you
Let me switch to, oh, where is it? Yeah.
yes.
Same thing.
So the Littlewood-Richardson coefficients we talked about at the end, they would, so you're working in the permutation. So lambda is a permutation. So you're not talking about the Littlewood-Richardson coefficients for Schubert polynomials that are indexed by elements of the symmetric.
Permutation.
Just
Oh, yeah. Right. I think for Schubert polynomials, it is not known.
Okay.
Yeah. That is so if you have this Schubert polynomial here with index permutation, the Schubert times Schubert It is known that it expands in terms of Schubert with a positive non-negative integer coefficient, but finding a combinatorial interpretation for this coefficient is a major open problem in algebraic combinatorics.
So this generalization doesn't recover that problem.
No, because it's just partitions.
Partition.
Yeah.
Okay, okay.
Right. Yeah.
Do you like have you done any type of experiment that shows if you get something interesting for different versions? Like when you specialize alpha and beta, you get the usual ones.
Mhm.
But do you know other values of alpha and betas where you get something interesting?
We haven't done much experiments on that yet. Yeah.
Okay.
All right. But I think that's a good idea. I think that's something that we should do, but we haven't done it yet.
And do you have do you have any geometric interpretation of these Grothendieck polynomials that depend on both alpha and beta?
No, that one we don't have, and I think it'll be really nice if you can find such an interpretation. But since I don't know much about this geometry or representation theory, we haven't done in that direction. But I really love to see geometry interpretations or representation theoretic interpretation.
I see.
For this.
Can you go back to the picture with the 3 or the 6?
6?
Back a bit. Yeah, that one.
This one. Yeah,
This one. So your polynomials would fit on the bottom left and bottom right, right?
Right. So here it generalizes all these to infinitely many parameters, and also if you set all the alphas to be 0, then it becomes this.
I see.
So it generalizes basically everything here. Also the dual version over here. Yeah.
So all 3 things have some geometric interpretation, right? So it's possible that your polynomials will also have one.
Oh, but this I don't know. I'm not sure.
Don't
This one may not have a geometric meaning. So maybe this will be the first step.
Okay.
What are the geometric meaning for others?
This one is for sure like a Schubert K-theoretic cohomology or like Schubert flat variety or something like that. This one is quite classical, so it's known. Actually, maybe these polynomials themselves, they may not have explicit geometric interpretations, but what I remember is that the motivation for them to study this was from geometry, like some kind of Euler, Brill, some curve, Euler characteristics of Brill. Oh yeah, that one. Yeah. I think they were geometers. The authors were geometers. Yeah. But I'm not sure. Maybe this polynomial may not have a geometric interpretation. Yeah, but it has some motivation from them.
Any other questions or comments? Yeah.
So I'm kind of curious in this whole story how special it is for functions to be symmetric. Like, for example, one could try to consider alternating functions, I guess, that'll change sign depending on the sign of the.
Oh yeah.
Or in general, you can define whatever group action on.
Yeah, right.
Yeah, and then on a set of polynomials and.
Right. That's a very good question. So symmetric functions are like, or symmetric, let's look at symmetric polynomials. They are like polynomials invariant on the symmetric action. So symmetric group is like a Cox group or reflection group of type A. So there are other studies of like invariant polynomials invariant under other group types like a type B, type C, and etc. So there are parallel stories of this. But type A is, of course, is a classical one, and it has simplest and like most beautiful. But for type, there are other studies, type B and etc. But it's more complicated. Yeah, but there are directions in this way. Yeah.
Like maybe no Young tableaus or.
There are Young tableau. Yeah, that they have like a tableau interpretations of this. Yes. but of course more complicated conditions.
Is there an accepted generalization of Grothendieck polynomials to type C, for example?
Then I don't remember, but there are some papers on this, type B or C, something like that. Yeah.
Any other questions or comments?
Very naive question. Sorry. What is what is a good thing about the Jacobi-Trudi formula? From this, what can you do? And
What is?
I mean, in the beginning, you talked about the high school problems.
Oh yes.
Yeah. So, but it's not related to high school problems, right? That is short polynomials. I mean, it's a
Right,
basis, but
yeah, it's not. It's not a high school problem. Yes.
yeah, right. So, and once you know this, what can you do?
I see. What can we do with this? First of all, I mean, once you have like symmetric polynomials, then one natural question is how can you write this in terms of other bases and stuff like this? So, for instance, show function, can we write this in terms of other basis element? So this gives you one answer to that. That's one thing. And also using this, there are some applications, if I remember correctly. For example, there is a quite well-studied object, symmetric polynomials called chromatic symmetric polynomials. So you have a graph. Suppose that you have a graph like this. Just like this. And then I'm going to color this. It's called a proper coloring. Proper coloring means you assign numbers here so that two vertices connected by an edge must have different colors. Like a 1, then you cannot put 1 here. 2, this is okay. 3, 3. This is a proper coloring. And for a proper coloring like this, okay, kappa, I'm gonna define the weight to be the x1 to the number of ones here, just like the semi-standard Young tableau stuff. You define, you can naturally define this monomial for each chromatic proper coloring, and summation of all proper coloring of a given graph and the weight. And by definition, if you permit the variables or numbers, there is still proper coloring. So it is a symmetric polynomial, symmetric function. And this is called a chromatic symmetric function. And this is very well studied object. And what's this is usually denoted by xg. And what's known is that this is a sure positive. That means if you expand this in terms of sure functions, then the coefficients are non-negative integers. And there is a very nice combinatorial interpretation for this. And it's due to Gasharov, like 30 years ago. And he used Jacobi-Trudi formula to prove this identity. So this is one instance. I think there are more.
So you can use this to understand the
Right.
some
Understand something. Right. Yes.
Any other questions or comments? All right, let's thank the speaker again.